This is a demonstration or tutorial of the Nerst equation and its implications to electrochemical cells. But we already know that Gibbs free energy and Le Chatelier's principle are tied together. Reactions that go forward or reverse and have a direction are spontaneous and have a negative delta G. So we know there's an implication or tie into positive volts. And we know there's a whole bunch of equations, and I've developed, or at least I derived many of these reactions for you in other lectures. So let's go and test out this Le Chatelier's principle, or the Nerst equation, which is again an application of delta G specifically for redox reactions. So taking a look at my reactions here, I have the Nerst equation on top. And as we look, we can see that the Nerst equation from its development is the E of cell, non-standard conditions, which really mean a lot to us because we're almost never at standard conditions, equal the E0 cell, which is from the standard tablature of net potentials, minus the gas law constant in joules times temperature in Kelvin over the ratio of electrons in a half reaction times Faraday's constant, the ln of Q. Now Q, of course, is products of a reactants. So we're going to put this to test and see how the non-standard conditions, which is how they differ from the voltage we get from standard conditions, which mean I have 1 mole of solutions, 1 atmosphere at 25 degrees Celsius. I'm not at these conditions. So we're going to deal with the Daniell cell today. The Daniell cell, at least I'll start this way, is I have a zinc electrode and a copper electrode. The zinc is better at oxidizing, and it has a reduction potential of negative 0.76, but I flipped the sign off my table so that it's now positive because it likes to oxidize. Copper is poor at oxidizing. It has a oxidation potential of negative 0.34, but its reduction potential, as written, I use. It likes to reduce. And if you notice, my Q, which is products over reactants, I only include the zinc plus 2, which is product here of the overall reaction. And this copper plus 2 I only use because that's my reactant. I don't include the zinc 0 or the copper 0 because they're solids, and solids don't have concentrations in your Q or your expression. So in any case, what I'm going to do here is we're going to look at this. Now we know the net potential should be 1.10 volts. That's what I get from my reduction potential tables when I add them together. I use the one that reduces, plus I flip the sign of the one that oxidizes, and I add them together, and I get a net potential. This voltage means the force. Now this has nothing to do with electrons. This is a pathway, and this tells us how well something oxidizes, pushes charge along, and how well something pulls charge along. This is a measure really of energy, joules per coulomb. So let's look at the Daniell cell real quick. And we're going to put this to test by changing the voltage, but let's see what I get. I do not have 1 mole. I would have to have 1 mole of zinc plus 2 ions and 1 mole of copper. So put my electrodes in. Here's going to be my anode. The zinc is better at oxidizing than copper on the reactivity series you possibly have learned. And so therefore, zinc is going to be the anode. The cathode is the place of reduction. Anox, red cat. You probably hopefully learned that. And now I'm going to plug in my leads to my voltmeter. This is my copper. This goes to my zinc, which is my anode, anox, oxidation. And if you notice, I get 0 volts because I did not put in my salt bridge. My salt bridge maintains electrical neutrality. And now I should get some voltage, 0.89. Now I'm supposed to get, as I've already have mentioned, I'm supposed to get that 1.1 voltage, okay? Right there by my thumb there. That's what I'm supposed to get if I had 1 molar solution of copper plus 2 and a 1 molar solution of zinc plus 2. So I'm not quite getting that. Now why? Well, part of the reason could be that if you look at my Q here, part of the reason could be that, well, if this is a negative expression, this is my E0 cell, this is the Nerst equation, this is going to stay pretty much constant, but the ln of Q is what I'm talking about. The Q is products over reactants. So the reason why I'm under 1.1 could be that my zinc concentration is greater than my copper plus 2. I mean, I eyeballed them. So if I'm under, it's probably telling me the zinc is what? Greater. Now if it's greater, this ratio, if I have a higher molarity of zinc plus 2 than copper plus 2, this Q is greater than 1. Now if it's greater than 1, the log, or the natural log of that number will stay positive, and that positive Q times a negative expression makes it a negative value overall, and therefore 1.1 minus a value gives me something less than 1.1. Okay? Now, But that's not what I'm going to do here. I'm going to test this by trying to change the concentrations from this position. So what I'm going to first do is I'm going to lower the amount of copper ions. So I'm going to dilute that. So what I'm going to do is take out the salt bridge. All right. And let's identify the current voltage, 0.9. All right. Now, I'm going to dilute the copper ions. So how am I going to do that? Well, very simply, I'm going to pour this beaker into another beaker. And I'm going to add some water. So let's add some water to it. The reason why I'm not doing it while it's connected is because of the salt bridge I have. Using a siphon, this would actually dilute this side. I don't want to dilute this side. So I want to dilute this. So I'm adding some water. And then I'm going to pour off the extra. Now concentration is independent of the volume. So I'm just going to get rid of this. And now I should have a diluted solution that's about the same level of where I was. Okay, I'm going to put in my electrode. Hopefully it doesn't fall off, as it did. Okay, got my electrode. And now, here's the moment of truth. It was 0.9, but by diluting it, I got 0.88. So it dropped. Now, why did it drop? Well, it dropped because what I was doing here was decreasing the copper plus 2 here while the zinc stayed the same. Now I have it going up, but if I was to decrease the copper and keep this the same, if I increase my denominator, this whole value gets bigger, right? Make the denominator, no, it's actually dropping further. So the Q is going to increase. I guess I needed to dissolve that or stir it. In any case, the Q is going to increase, which means this whole expression, right, becomes a larger number and a larger negative number because something's in front, that negative sign. So I made the Q bigger by making my denominator smaller, which made this a larger number. And of course, because I've got the negative in front, it's a bigger number that I'm subtracting, and it gets smaller. And there's an application of changing the concentration. Now, there's more that I could talk to you about this. If I look at the overall reaction, because you can look at the Nerst equation, but you also can look at it in terms of the overall equation. So if I look at the overall equation, so I knock that over, all right, the overall equation, if I lower the copper plus 2, which is a reactant, we know from the Shetler's principle the reaction is going to shift to make more of it. Or if we lower the reactant, we do what? We make Q larger than K, and the reaction shifts to reach equilibrium. Either way, we're making the forward reaction less spontaneous, and the voltage has to drop by that way. All right? Now, I'm not sure what's happening here, but now I'm back to 0.87. But clearly, I started at point what? 0.9. All right, let's do something else. What if I increase the concentration of my zinc ions? Now, let's go back to where I was. Now, if I increase my concentration of my zinc ions, where am I? All right, here I am. So if I increase my concentration of my zinc ions, I also make Q bigger. Then, therefore, this becomes a bigger negative, and we should go down. So by increasing the zinc concentration, a bigger negative expression. So let's add some solid zinc nitrate. Nitrate's going to be our what? So we're at 0.87, and now I'm looking to go lower, just by adding more zinc plus 2. If I stir a little bit, maybe I can make it go down. And it is. It's going down. So I'm increasing the concentration of something, and it's going down. I decreased, it went down. Why? Again, let's go back to our equation. I'm really increasing Q. Right? I'm increasing Q. That's trying to go back on me. But again, I'm increasing zinc, which is on top, which is the product. Therefore, the Q, of course, is going to get bigger. Now, of course, it's making a liar out of me as it's going up and down. But as I dissolve it, okay, at some point, as this gets concentrated, it does drop. Now, it's not a drastic drop. It's subtle, but it's there. Okay? Now, let's end this off with a concentration cell. So, take this apart. Pull out my salt bridge. Let's make a concentration cell. What does that mean? Well, I'm going to use, guess what? I'm going to use zinc, and I'm going to use zinc to be my electrodes. And I'm going to build a cell just on concentrations alone. So what I'm going to do is I'm going to have my concentrated to the right and my dilute concentration to the left. And I'm going to add some solid here. Add a little bit here to make it not as concentrated. We're going to add our water to about the same volume. And I'm estimating here, I'm eyeballing. It's a little bit of demonstration. I need the top to be off the pour though. So I'm here and I'm here. I'm just trying to make sure my salt bridge doesn't work as a siphon. Okay, I'm going to stir. And it's kind of interesting. I'm going to make a battery of the same contents. Just by changing the concentrations, I should be able to make a voltage or a potential difference. So let's do that. So I'm essentially dissolved here. This is the more concentrated. Definitely I added more here to the same volume. We're going to put in our salt bridge. And I'm going to put the anode side, or the lead that I think is the anode, to the dilute solution. And I'm going to put the cathode side, or the what I think is going to be the cathode, on the concentrated side. And what I have is I have almost a concentration, maybe, making a liar out of me, 0.28. I've created a concentration cell. Look at that. How did that happen? How did I make a voltage? Now, it's not as great as the others, but I definitely made a volt. I definitely made a concentration cell. Now, how did that work? Well, here we go. So let me explain what's happening here. I've got a voltage, and it's working. And what I have here is no net reaction, which is strange. It's not a reaction at all. We should get a 0. Positive 0.76 for the oxidation, negative 0.76 for the reduction. Okay? Although I probably, this should be a negative and positive, but anyway, it would be 0. Now, plug it into the Nerst equation, we would get 0 for our E0 cell. Now the question is, this is creating the voltage. We're going to go to 0. Now obviously, if we get a voltage, my Q's got to get smaller, right? I've got to get so small that my natural log of this number is less than 1, and it becomes negative. Anything less than 1 for a log becomes negative, like 1 times 10 to the negative 1 is a tenth. But that negative 1, since a natural log is a logarithm, becomes negative. And this becomes a negative number. Therefore, this becomes a negative, and a negative makes a what? A positive value that we add to 0 to make it greater than 0. So this has to be smaller than 1. Q's got to get smaller than 1 so that this can be negative. Now, how can that happen? Well, if I decrease the zinc plus 2. Now, this zinc plus 2 has to be decreased. Now, where is it? Well, it's right here. So I got to decrease one of the products. So where zinc oxidizes, I have to decrease it. Look, zinc is oxidizing over here. This is my anode. So that is where, okay, it is being decreased. And I have to increase what? One of the reactants. This zinc plus 2 is where there's what? Reduction. That occurs at the cathode. That's my cathode. So that's where this is concentrated at my cathode. And why? Making this bigger, okay, this bottom number gets what? Bigger. This value gets smaller. Or when the zinc plus 2 gets what? Bigger, gets smaller, this from the what? I made this dilute. It drives this number smaller. So I'm increasing the concentration of the zinc plus 2, okay, in the cathode region, and I'm decreasing the concentration of the zinc plus 2 in the product or the anode, and that creates a differential or some number that's smaller than 1, makes this a negative number times this negative, and I add a positive value to 0, and that's how I get positive volts. Of course, our voltage is going down because this is slowly, as most spontaneous reactions, working toward equilibrium. So even though voltage is going this way, or I'd say some current is, okay, not very much, but the reverse reaction is starting to occur and making this less spontaneous. So what's happening is we're running out of our reactants. We're going forward, and zinc plus 2 is going down. which is making this less positive, therefore our voltage is dropping.